Welcome to the deep dive. Today we're diving straight into something that's becoming really essential for anyone using AI prompt engineering. Think of it as the kind of secret sauce to getting large language models like Gemini to give you exactly what you need. I mean, anyone can type a question, right?
Sure, yeah.
But knowing how to really craft those text inputs, that's where the magic happens, turning okay results into, truly insightful and accurate ones.
Absolutely. It's really the difference, isn't it, between just a vague request and a precise instruction.
Yeah.
And to help us navigate this pretty fascinating area, we're drawing on a comprehensive guide. It's from February 2025, put together by Lee Boonstra and a whole team of experts. Michael Sherman, Yuan Cao, Eric Armbrust, Anna Nawalgaria, Antonio Gulli, and Simone Camel.
Quite the lineup.
It is. So consider this our kind of fast track to understanding how to effectively communicate with these powerful AIs.
Exactly. Our mission today is to pull out the crucial techniques and best practices from this guide so you, our listener, can immediately start getting better results from LLMs, even if you don't consider yourself like a tech expert.
Right.
We're talking about using prompts to summarize stuff, extract key details, get answers, write code. I mean, the possibilities are huge.
They really are.
Okay, let's unpack this. The guide kicks off by looking at something beyond just the words we type, how we can actually configure the LLM's output itself.
Yeah, what's fascinating here is that before we even get to the art of crafting the perfect prompt,
Right.
we have some fundamental controls over how the LLM will generate its response.
Okay.
One of the first things to think about is output length, which is basically the number of words, or, more accurately, tokens the model will produce.
Right, tokens.
It's a bit of a balancing act, really. More tokens can mean a more detailed answer, but it also takes more processing power. Might cost more if you're using a paid service.
And takes longer, I guess.
And can take longer, yeah. Plus, if you set the limit too low, your brilliant answer might just get cut off mid-sentence.
Okay. That's annoying.
It can be. And this becomes really important for some of the more advanced techniques we'll talk about later, like React.
Okay, so it's like telling the AI, give me a detailed answer, but, not a novel.
Pretty much, yeah.
Now, the guide then talks about sampling controls. That sounds a bit more under the hood. What's the basic idea there?
Think of it like this. When an LLM generates text, it doesn't just pick the absolute most likely next word every single time.
Oh, okay.
Instead, it looks at a whole range of possible next words and assigns probabilities to each one. Those sampling controls, and the main ones, are temperature, top K, and top P. These are basically knobs we can turn to influence how the model actually chooses that single next word from all the possibilities.
Temperature sounds interesting. Is that about making the output more predictable or, more surprising?
Exactly. Temperature essentially controls the randomness, you could say, in the model's word selection. A lower temperature, so closer to zero, makes the model more predictable and focused. It's going to consistently pick the words with the highest probability.
Which is good for facts.
Generally, yeah.
Yeah.
That's what you want for factual tasks or anything where you need a straightforward answer.
Yeah.
But crank up the temperature and the model gets more adventurous.
More creative.
More creative, more varied outputs, exactly. The guide even touches on the math behind this, mentioning the softmax function. That's how the model calculates those probabilities.
Okay.
So a low temperature makes the highest probability really stand out, while a high temperature kind of flattens the curve, making more options seem plausible.
So low temperature for getting facts straight, high temperature for brainstorming creative ideas. Got it. Now, what about top K and top P?
Okay, so these are two other ways to narrow down the choices to the next word. Top K sampling tells the model to only consider the K most likely next words.
K being a number.
Yeah, K is just a number you set. So if you set K to, say, 10, the model will only pick from the top 10 most probable options. A higher K gives the model more room to be creative, while a lower K makes the output more focused, more predictable. And if you set K to just 1...
That's most predictable.
That's the most predictable, yeah. That's what they call greedy decoding, which we kind of mentioned with temperature 0.
And top P, how's that different?
Top P, which is also known as nucleus sampling, works a bit differently. It looks at the cumulative probability of the next words.
Cumulative, okay.
So you set a probability threshold, let's say 0.9 or 90%. The model then looks at the most probable words and adds up their probabilities until they reach that 90% threshold. It then chooses the next word only from that set of words. So if you set a high P, you're allowing for more diverse words to be chosen.
More options.
More options, yeah. While a low P restricts it to the most probable and therefore more predictable options, a P of 0 is also that very deterministic, greedy decoding again.
Okay.
The guides suggest that the best way to find the right balance is often to just play around with both top K and top P, see what works best for your specific task.
Okay, so they're both about limiting the choices, but in slightly different ways. How do they all work together if you have temperature, top K, and top P all active?
That's a great question, and it's important to understand how they interact. If all three are enabled, the model first filters the potential next words based on both the top K and top T criteria.
So it has to pass both tests.
Exactly. Only the words that make the cut for both are then considered. After that initial filtering, the temperature setting is applied to the smaller set of candidate words to finally select the next one.
Right.
If only some of these settings are available, the model just uses the ones that are provided. And interestingly, if temperature isn't an option, the model will just randomly pick from the words that pass the top K and or top P filters.
That makes sense. It's like having multiple filters to kind of refine the output. Now, the guide also gives us some starting recommendations for these settings, which is super helpful.
Yes, it does. For results that are generally coherent, but still have a bit of creativity, they suggest starting with a temperature around 0.2, a top P of maybe 0.95, and a top K of 30.
Okay, that's a good baseline.
Yeah. And if you really want to push the creative boundaries, you could try something like a temperature of 0.9, a top P of 0.99, and a top K of 40.
Wow. Okay. Higher numbers there.
Definitely.
Yeah.
On the other hand, if you're looking for less creative, more factual responses, a starting point of temperature 0.1, top P 0.9, and top K 20 is recommended.
Lower numbers across the board.
Right. And this is crucial. For tasks where there's really only one correct answer, like solving a math problem or something.
Yeah.
The guide strongly advises setting the temperature to 0. Make it as deterministic as possible.
Zero randomness. Got it. Those are great starting points to keep in mind. Now, there's also a warning in the guide about something called the repetition loop bug. That sounds annoying. What's that all about?
It is indeed. It's a pretty common issue where the LLM gets stuck in a rut, and starts repeating the same word or phrase or even whole sentences over and over again.
Like a broken record.
Exactly like a broken record. The guide explains that this can unfortunately happen with both very low and very high temperature settings.
Oh, both. That's weird.
Yeah, and also with different top K and top P values. At low temperatures, the model can become too fixated on the highest probability path. And if it circles back to something it already generated, it might just repeat it.
Okay.
And at high temperatures, the increased randomness can sometimes, just by chance, lead the model back to a prior state, causing it to loop. So it's a good reminder that carefully tuning these sampling parameters is really key to getting the output you want without the AI getting stuck.
Okay, so it's all about finding that sweet spot to avoid the loops. Now let's dive into what most people probably think of when they hear prompt engineering, the actual techniques for crafting those text inputs. The first one mentioned is general prompting, or zero shot. What's the deal with that?
Zero-shot prompting is basically the most straightforward approach. You essentially just give the LLM a description of the task you want it to do.
Just the instruction.
Just the instruction, yeah. Without providing any examples of the desired input and output, the term zero-shot literally means no examples.
Makes sense.
The guide highlights the importance of documenting your prompts clearly, even for zero-shot. They have this table 1 showing an example where they prompt Gemini Pro to classify a movie review, something like, Her is a disturbing study, as positive, neutral, or negative.
Okay.
And with a low temperature, 0.1, the model correctly identifies it as positive.
Interesting. So even without showing it examples, the model can often figure out the task and give a decent answer.
Often, yes.
But what happens when zero shot isn't quite cutting it? That's where one shot and few shot prompting come into play, right?
Exactly. When you want to steer the model towards a specific way of structuring its output, or maybe following a particular pattern, providing examples can be incredibly beneficial.
Like teaching it by showing.
Precisely. A one-shot prompt includes just one input and its corresponding desired output, while a few-shot prompt gives the model several examples.
How many is few?
Well, the guide suggests aiming for around 3 to 5 usually. But that can vary a lot depending on how complex the task is and also, the limitations of the model's input length. You can't give it too many.
Right, character limits.
Exactly. The idea is that these examples act as a kind of mini training session, showing the model what you're looking for and helping it understand and complete the task better for new, unseen inputs.
The guide provides a few-shot example in Table 2 where they're trying to parse pizza orders into a JSON format. Can you walk us through how that works?
Absolutely. So the goal there is to take a natural language description of a pizza order. Someone just typing what they want.
Like, I want a large pepperoni.
Yeah, exactly. And convert it into a structured JSON format, which is really useful for processing data automatically.
Okay.
So the prompt starts by giving two clear examples. The first shows an order like, I want a small pizza with cheese, tomato sauce, and pepperoni. And then it shows the JSON output it should produce with fields like size, sauce, toppings.
Okay, clearly laid out.
Very clear. The second example demonstrates a more complex order, maybe a half-and-half pizza, and its JSON representation.
Got it.
Then, after showing these examples, the prompt presents a new order. Now, I would like a large pizza with the first half cheese and mozzarella, and the other tomato sauce, ham, and pineapple.
Tricky one.
A bit trickier, yeah. But because the model has seen the pattern in the examples, it's able to correctly parse this new, slightly more intricate order into the right JSON structure.
That's really powerful. It's like showing the AI how to think by giving it a few worked examples.
It really is.
And the guy really emphasizes that the quality of these examples matters a lot.
Oh, absolutely. The guide stresses that your examples should be highly relevant to the task. They should cover a diverse range of possible inputs, and they need to be accurate.
Accuracy is key.
Definitely. Even a small error in an example can confuse the model and lead to, well, less desirable results. Furthermore, if you want your model to handle all sorts of inputs, even unusual ones.
Like edge cases.
Exactly, edge cases. It's a good strategy to include those in your examples.
Yeah.
These less common or slightly tricky inputs can help the model learn to be more robust.
Okay, next up we have system, contextual, and role prompting. These sound like different ways to give the LLM some extra guidance beyond just the main question or task.
You've got it. These techniques are all about influencing how the LLM generates text by setting different kinds of context. System prompting is about establishing the overall context and purpose for the model.
Like setting the stage.
Exactly, setting the stage for the whole interaction. You can use system prompts to define the broad task the model should be doing, like translation or classification, or maybe to enforce specific requirements on the output format or style.
The guide gives an example of system prompting in Table 3, where they force the output to be in uppercase.
Yeah, just shouting everything.
And then in Table 4, they specify that the output should be in JSON format. Why is that JSON example particularly useful?
Well, the guide highlights several key advantages of using JSON as an output format, especially when you're trying to extract data.
Okay.
It points out that in real-world apps, you can often get the data back nicely structured, even sorted, which is great for lists or events over time. But more importantly, by explicitly asking for JSON.
You're giving it structure.
You're imposing a clear structure on the response, exactly. And this can actually help to reduce those hallucinations we talked about, where the model might just invent information.
That makes perfect sense. Structure leads to more reliable data. Now, what about role prompting?
Role prompting is fun. It involves assigning a specific persona or identity to the LLM.
Like telling it to be a pirate.
You could, although maybe not for serious tasks. But yeah, this helps the model generate responses consistent with that role, tone of voice, writing style, even the kind of knowledge it's expected to have.
Okay.
The guide has a great example in Table 5 where the model acts as a straightforward travel guide for Amsterdam recommending museums.
Standard stuff.
Pretty standard. Then in Table 6, the role is still a travel guide, but with the added instruction to be humorous and inspirational when recommending things in Manhattan.
And the output changes.
Dramatically.
Yeah.
The tone and style are completely different. So the key takeaway is that defining a role gives the model a clear framework for how to approach the task. The guide even lists some effective styles like confrontational, descriptive, formal, humorous, persuasive. Lots of options.
So you're essentially telling the AI, imagine you are this kind of person with this kind of voice, and then answer my question.
Pretty much, yeah.
And then there's contextual prompting. How does that differ from system and role prompting?
Contextual prompting is all about providing specific background information that is directly relevant to the particular task you're asking the LLM to do right now.
More specific than the overall system prompt.
Exactly. This context helps the model understand the nuances of your immediate request and tailor its response much more accurately. Table 7 in the guide gives an example where the context is set as writing for a blog specifically about retro 80s arcade games.
Very niche.
Very niche. And given that context, the prompt asks for 3 article topic suggestions with brief descriptions. And the model generates ideas totally in line with that very specific theme.
Okay, so system prompts set the overall framework, role prompts define a persona, and contextual prompts provide the immediate background info for the current request. That clears things up. The next technique is step-back prompting. This one sounds a little bit unusual.
It might seem a bit counterintuitive at first, yeah. But it can be surprisingly effective for certain types of problems. Step-back prompting involves first asking the LLM a more general, related question before you ask the specific question you're actually interested in.
Why would you do that?
The idea is that this initial step-back allows the LLM to access and process relevant background knowledge and broader reasoning patterns that it might not engage if you just jump straight to the specific task. It primes the pump, so to speak.
The guide uses an example of trying to write a storyline for a first-person shooter game. How does this step-back approach improve the outcome there?
Okay, so Table 8 shows a direct traditional prompt asking for a game storyline. And the output is, well, it's fairly generic, not super exciting.
A bit bland.
A bit bland, yeah. Then, Table 9 demonstrates the step-back prompt. Instead of asking for the storyline directly, it first asks for, 5 fictional key settings that tend to contribute to challenging and engaging storylines in popular FPS games.
Okay, so asking about common themes first.
Exactly. The model comes up with a list of diverse settings, an abandoned military base, a cyberpunk city, things like that. Then finally, in Table 10, the original storyline prompt is used again, but this time it includes that list of engaging themes generated in the step-back prompt as additional context.
And the result?
The resulting storyline, it's about an underwater research facility facing some mysterious threat, is much more detailed, much more imaginative and evocative. It really seems that initial step-back helped the model tap into more creative and relevant ideas.
That's a really clever way to prime the model's thinking. Next, we have chain of thought, or CUP prompting, which has been getting a lot of buzz lately. What's the core principle behind it?
Chain of thought prompting is a technique that aims to significantly improve the reasoning abilities of LLMs, especially for more complex problems.
How does it work?
It works by explicitly prompting the model to generate a sequence of intermediate reasoning steps before it arrives at the final answer. Basically, you ask it to show its work.
Like in math class.
Exactly like in math class. This encourages the model to break down the problem into smaller, more manageable chunks. The guide highlights several key advantages. It's relatively easy to do.
Okay.
It's proven to be very effective. It works well with off-the-shelf LLMs. And it gives you some interpretability because you can see the model's thought process.
That's useful.
Yeah. And it seems to make the model more robust to variations in how you phrase the prompt. The main downside?
Let me guess. More tokens.
Got it. Generating those intermediate steps naturally increases the output tokens, which means higher costs and longer processing times.
Trade-offs. Always trade-offs. The guide uses the simple age calculation problem in tables 11, 12, and 13 to really illustrate the power of COTI. Can you walk us through that?
Absolutely. So table 11 shows a direct prompt asking for someone's partner's age based on some past relationship info and a current age. The LLM, without any prompting for reasoning, actually gets the answer wrong.
Oops.
Yeah. Then in table 12, the prompt is subtly changed to include the phrase, "Let's think step by step."
Just adding that phrase.
Just adding that magic phrase. This prompts the model to explicitly show its reasoning, breaking down the problem, calculating the age difference, applying it to the current age, and boom, it gets the correct answer.
Wow.
Table 14 then shows a single-shot code example where a similar age problem is provided along with its step-by-step solution, as an example, before the target problem. This further reinforces the reasoning process and also leads to a correct answer for the new problem.
It's remarkable how simply asking the AI to think step by step can have such a dramatic impact on accuracy for these kinds of tasks.
It really is.
The guide also mentions that COTI can be particularly useful for things like generating code and creating synthetic data.
Yes. The guide suggests that basically any task that you yourself might solve by talking through the steps is a good candidate for chain of thought prompting.
If you can explain it logically.
Chances are you can use COTI to guide an LLM to do the same, yeah.
Okay. Building on the idea of chain of thought, we have self-consistency. This sounds like a way to make that reasoning even more reliable.
Exactly. While code is fantastic, it often relies on just a single path of reasoning. Self-consistency takes this a step further. It generates multiple different reasoning paths for the same prompt.
How does it get different paths?
typically by using a slightly higher temperature setting to encourage more diverse thinking, more randomness in the steps.
Ah, okay.
It then looks at all the final answers from these different reasoning attempts and selects the most consistent one, the one that appears most often through a process of majority voting.
Like getting a second, third, fourth opinion from the AI.
Precisely. And this can significantly improve the accuracy and overall coherence of the final answer. The trade-off, as the guide points out, is again costlier generating multiple responses.
Right. More computation. The guide illustrates this with an email classification example in Table 14. How does self-consistency help there?
So the email in the example has some ambiguous language, maybe some sarcasm. When a standard zero-shot code-T prompt is sent to the LLM multiple times,
it might give different answers.
Exactly. It might come up with the different reasoning steps and even different final classifications, sometimes labeling it important, other times not important.
Not ideal.
Not ideal. Self-consistency aims to fix this uncertainty. It has the model generate several of these reasoning attempts. Then it looks at the final classifications from all of them, and the one that appears most frequently is chosen as the most likely correct answer.
So it finds the consensus.
It finds a consensus, yeah. Increasing the confidence in the final result. The process is basically generate diverse paths, extract the answers, pick the most common one.
That's a really interesting way to get a more robust answer. Then there's tree of thoughts, or TOER-T. How does that compare to the more linear chain of thought?
Tree of thoughts is described as a more generalized version of chain of thought. Instead of exploring just a single sequence of reasoning steps.
Like COTI does.
Right. TOER-T allows the LLM to explore multiple different reasoning paths simultaneously, almost like branching out in a tree.
Yeah.
At each step, the model can consider several different possible next thoughts and evaluate which ones seem most promising for reaching the final solution.
So it explores more possibilities.
A lot more possibilities. It's particularly well suited for tackling really complex problems that might require exploring different avenues and maybe even hitting some dead ends before finding the right path.
Gotcha. And then we have REACT, which stands for Reason and Act. This sounds like it involves the LLM doing more than just generating text.
Exactly. REACT prompting takes things to another level. It combines that natural language reasoning, like in chain of thought.
The thinking part.
The thinking part, yeah. But it combines it with the ability for the LLM to interact with external tools.
Tools? Like what?
Could be anything, really. A search engine, a calculator, a code interpreter. This approach mimics how we humans often solve problems, right? We think through the steps, then we take actions to gather more info or try things out.
Makes sense.
The guide notes that REACT has shown really good performance across a wide range of different task types.
The guide provides some Python code snippets 1 and 2, to illustrate REACT in action. What's going on in that example?
So, the example uses the LangChain framework with Vertex AI to set up what's called a REACT agent. The prompt asks a question that needs outside info. How many kids do the band members of Metallica have?
Okay, something it wouldn't just know.
Right. So the agent goes through a series of thought-action-observation loops. First, it thinks about what's needed to act. Okay, I need the members of Metallica and how many kids each has.
Logical first step.
Then, the next step is an action. It uses a search tool to try and find this info online. The observation is the result it gets back from the search.
The search results.
Yeah. Based on this new information, it updates its reasoning, thought, and plans the next action, maybe another search to clarify something or find info on another member. This cycle of think, act, observe continues until the agent has gathered enough information to confidently give the final answer, which in this case is that the members of Metallica have a total of 10 children. The guide does highlight that in practice, you often need to send the previous prompts and responses back to the model to maintain the context.
Keep track of the conversation.
Exactly. And provide clear examples and instructions for how the agent should use the tools.
That's a really powerful concept, the AI not just thinking, but actively going out and getting the information it needs.
That's pretty cool, yeah.
Finally, in terms of prompting techniques, we have automatic prompt engineering, or APE. This sounds like the AI is actually helping us write better prompts.
That's precisely the idea.
Yeah.
ATE is a method for automating the often tricky process of creating really effective prompts.
How does that work?
Well, the basic process involves prompting another language model to generate multiple candidate prompts for a specific task you have in mind.
So you ask an AI to write prompts for another AI.
Pretty much. Then these generated prompts are evaluated using some kind of metric. The guide mentions things like BLEU and Rouge scores, which are common ways to measure the quality of generated text.
Okay.
The best performing prompts are then selected, or maybe even further refined. The guide gives an example of using this to generate different ways a customer might phrase an order for, say, a Metallica t-shirt when talking to a web shop chatbot.
So generating variations of user input.
Exactly. By automatically generating and evaluating these different phrasings, you can create a chatbot that's much more robust and better understands the diverse ways people might actually ask for the same thing.
That's truly meta, using AI to optimize how we talk to AI. Now, the guide also includes a dedicated section on code prompting. How does using prompts for code-related tasks differ from the general prompting techniques we've been discussing?
Well, while the underlying large language model is still the same, code prompting specifically focuses on using prompts to help with tasks related to software development.
Like actually writing code.
Like generating new code, yeah. But also explaining existing code, translating code from one language to another, and even debugging and reviewing code. The guide provides several practical examples using Gemini Pro within Vertex AI Studio to show these capabilities.
Can you give us a couple of examples of how these code prompting techniques work?
Certainly. So Table 16 shows a prompt that asks for a bash script to rename all the files in a folder by adding the prefix draft to each file name.
A common sysadmin task.
Exactly. The model successfully generates well-documented and functional bash code that does this. Then Table 17 takes the same bash script, but this time without any comments.
Strips out the explanations.
Right, and prompts the model to explain what the script does. The result is a clear step-by-step explanation of the script's functionality.
That's handy for understanding old code.
Very handy. Table 18 then demonstrates code translation by asking the model to convert that same bash script into Python.
And it does it.
Does it successfully, yeah. Finally, Table 19 shows a really useful application, debugging and reviewing. It provides a deliberately broken Python script along with the error message, the traceback.
Okay, the standard error output.
Yep. And the prompt asks the model to find the error and prove the code. The LLM not only correctly spots and fixes the error, it was an undefined function to uppercase.
Common mistake.
Common mistake. But it also suggests several other improvements to make the code more robust and readable. Things like handling file extensions better, dealing with spaces and folder names, using f-strings, adding error handling.
So it doesn't just fix, it improves.
Exactly. It acts like a helpful code reviewer.
It's pretty incredible how these LLMs can assist with so many different stages of the software development process. The guide also briefly touches on multimodal prompting. What's the key distinction there?
Multimodal prompting goes beyond just using text as the input.
Okay.
It involves using multiple different types of input together, like combining text with images or audio or other kinds of data to guide the model's response.
So the prompt itself isn't just text.
Right. This is different from the code prompting we just talked about,
Yeah.
where the prompt is still text, but the output is code. Multimodal models can understand and generate content based on this richer mix of inputs.
Okay, that makes sense. Now, to bring everything together, the guide concludes with a really valuable section on best practices for prompt engineering. What are some of the most important takeaways from that?
This section is packed with essential advice, really. One of the most emphasized points is, again, provide examples whenever you can. One shot, few shot. It's just a really effective way to show the model what you want.
Teach by example.
Exactly. They also strongly recommend designing with simplicity. Use clear, concise language in your prompts. Avoid adding unnecessary fluff that could just confuse the model.
Keep it clean.
Keep it clean. Being very specific about the output by providing enough detail in your sister or contextual prompts is also crucial for guiding the model towards a desired format and content.
Don't be vague about what you want back.
Definitely not.
The guide also makes an interesting point about instructions over constraints. Can you tell us more about that?
Yeah. The research seems to suggest it's generally more effective to tell the model what it should do, give clear instructions, rather than what it shouldn't do, imposing negative constraints.
Why is that?
Well, positive instructions tend to directly communicate the desired outcome more clearly. Negative constraints can sometimes be less clear, or they might even unintentionally limit the model's creativity in ways you didn't expect.
So focus on the positive.
Generally, yes. Of course, constraints are still important sometimes, especially for things like safety or preventing harmful content.
Right. Guardrails are needed. What are some other key best practices the guide highlights?
Okay, let's see. It advises you to control the max token length, either in the configuration or by explicitly asking for a certain length in the prompt to manage the output size.
We talked about that earlier.
Yep. Using variables in prompts is fantastic for making them reusable and dynamic, especially if you're building them into applications.
Like placeholders.
Exactly, like placeholders. Experimenting with different input formats and writing styles, asking the same thing as a question versus a statement versus an instruction, can sometimes yield surprisingly different and useful results.
Worth trying different phrasings.
Definitely. For classification tasks using FewShot, it's generally a good idea to mix up the classes in your examples. Don't put all the positive examples first, then all the negative ones. Mix them up to avoid bias based on order.
Good tip.
And since these models are always being updated,
they change fast.
They do. It's important to adapt to model updates. Try out newer versions, adjust your prompts, see if you can leverage new capabilities.
Stay current.
Exactly.
The guide also has some specific recommendations about working with different output formats, particularly structured formats like JSON.
Yes, definitely. For tasks that aren't just creative writing like extracting specific info, the guide strongly recommends experimenting with output formats like JSON or XML.
We mentioned JSON's benefits earlier too.
Right. It provides consistent structure, focuses the output on data, can reduce hallucinations, represents relationships, supports data types, it's easily sortable. Lots of good reasons.
Makes data processing easier.
Much easier. They even briefly mention tools for JSON repair in case the output gets cut off mid-JSON due to token limits and becomes invalid.
Handy for fixing broken output.
Yeah.
And what about when you're dealing with more complex data structures?
The guide introduces the concept of working with schemas, specifically using something called JSON schema.
Schema. Like a blueprint.
Exactly like a blueprint.
Yeah.
You use it not just to define the desired output structure, but you can also use it to structure the input you provide to the LLM.
Structure the input too.
Yeah. By clearly defining the expected format and data types of your input JSON, you give the LLM a much clearer understanding of what information is important and how it's organized. This can lead to more accurate and relevant responses.
That sounds like a way to provide even more precise guidance. Are there any final best practices we should touch on?
A few more key ones. The guide suggests experimenting together with other prompt engineers. Get different perspectives, bounce ideas off each other. It really helps improve quality.
Collaboration helps.
Definitely. For chain of thought, they recommend putting the final answer clearly after the reasoning steps. Make sure it's easy to extract, and often set the temperature to 0 round for more focused reasoning.
COTI specifics, got it.
And perhaps most importantly, they strongly advise you to meticulously document the various prompt attempts you make.
Keep detailed notes.
Very detailed notes. They even provide a template for a Google Sheet to track everything. Prompt name, goal, model used, the configuration settings, the full prompt text itself, the output you got, the model version, whether it worked, or sometimes okay, your feedback.
Wow, comprehensive.
Yeah, and even a link to the save prompt in a platform like Vertex AI Studio if you're using that. For ag systems, also document things impacting the retrieved content. The bottom line is, prompt engineering is fundamentally an iterative process. Experiment, analyze, refine, document, repeat.
That's an incredibly comprehensive overview of prompt engineering. It's clear that while it might seem simple on the surface, there's a real depth here, isn't there? A lot to learn about how to effectively communicate with these powerful AI models.
There really is.
We've covered so much today, from understanding those underlying controls like temperature and output length, to exploring a whole raft of prompting techniques. Zero-shot, few-shot, system, role, contextual, step back, chain of thought.
Self-consistency, tree of thoughts, react, even APE.
Right, and the specifics of prompting for code, plus all those essential best practices.
Absolutely. Mastering prompt engineering is truly an ongoing journey. It's all about experimentation, analysis, refinement, and as you said, we've really just scratched the surface of the knowledge in this guide.
So the next step is?
The next crucial step is for you, our listener, to take these ideas and just start experimenting. Try them out, see what works best for your specific needs and the tasks you're hoping to tackle with these incredible tools.
And on that note, here's a final thought to ponder. Considering the speed at which these large language models are evolving, how might these fundamental principles of effective communication adapt and transform in the future of human-AI interaction? What new forms of language or interaction might emerge as we continue to deepen our dialogue with artificial intelligence? Thanks for tuning in to this deep dive.